Let's think about this for a second. How do you design something like a supersonic jet or a super quiet submarine? I mean, you're fighting against things you can't even see, the wild, chaotic dance of air and water. And figuring out how to master those invisible forces? Well, that's one of the biggest puzzles in all of modern engineering. All right, let's get into it. So here's what we're going to cover. We'll kick things off with the billion-dollar question that keeps engineers up at night. Then we're going to step into what's called a digital wind tunnel to see how they simulate reality. We'll talk about why getting the blueprint right is so important, how they actually grade the performance of their designs, and then we'll see it all come together to build a better jet engine. Finally, we'll take a peek at what the future holds.
You know, at the end of the day, it all boils down to one word: efficiency. Making a jet engine even a tiny bit more efficient can save millions of dollars in fuel. But finding that little improvement it's incredibly tough. And why? Because you can't just wing it.
So this is it. This is the big question. Engineers know for a fact that better designs are out there. They're possible. But how do you actually find them without, completely blowing the budget?
And there's the catch, right? The multi-million-dollar catch. Building physical prototypes, testing them, watching them fail, and starting over, it's just way too slow and ridiculously expensive. That kind of trial and error is basically a relic of the past. There has to be a smarter way to do this. And that smarter way, of course, is to build it all digitally first. This is where we step into the amazing world of high-powered computer simulation, a field that has totally changed the game for modern engineering.
The main tool they use is called computational fluid dynamics, or CFD for short. Now, I love this analogy of a digital wind tunnel. It's perfect. Instead of building a real model and putting it in a real wind tunnel, you build a virtual one on a computer and hit it with simulated air. It lets you literally see the invisible. You can predict how it's going to perform and spot problems before you've even spent a dime on materials.
But here's the thing. A simulation is only as good as its blueprint. Garbage in, garbage out. In CFD, that blueprint is called a mesh or a grid. And making sure that that grid is actually reliable, well, that's a massive challenge all on its own.
Okay, so take a look at this propeller. It looks pretty simple, right? But the way air flows around those curves is incredibly complex. To simulate it, you have to break down the entire space around it into millions, sometimes billions, of tiny little cells to do the math. It's intense. And this brings us right to the heart of the problem. It's the question that every researcher in this field has to ask. If I run a simulation and get an answer, how do I know it's the right answer? How can I be sure that my digital test is going to match what happens in the real world?
Well, the old school methods for checking your work were often really rigid and super time-consuming. But there's a newer approach called the fitting method that's a real game changer. It's designed to handle the messy, complex shapes of real-world parts, like that propeller. It gives you a reliable answer without the insane cost of running simulation after simulation on finer and finer grids.
And here is the proof. Just look at this. The blue line is what the simulation predicted for thrust and torque using this fitting method. The green line, that's the data from an actual physical experiment. The match is it's fantastic. This is what validation looks like. This proves that the digital blueprint is trustworthy.
Okay, so we've got a simulation we can actually believe in. That's huge. But now, how do we use it to measure if a new design is any better? We need some kind of universal report card, a single score that tells us how we're doing.
In this world, that report card is called isentropic efficiency. Now, don't let the complicated name fool you. The idea is actually pretty simple. It just measures how close your real-world machine is to a theoretically perfect, 100% efficient, totally frictionless version of itself. So the closer you get to a score of 100, the better your design is. And it's not a one-size-fits-all kind of thing either. Engineers have different ways to calculate this score depending on what they're looking at. If you're grading something active that does work, like a turbine, you use one method. If you're grading something passive, like a nozzle, you use another. Choosing the right scorecard is absolutely key.
All right, let's put all these pieces together now. We've got a reliable way to simulate, and we have a precise scorecard to measure efficiency. So let's go back to that billion-dollar question and see how this all helps us build a better, lighter, more powerful jet engine.
What you're looking at here is a digital model of something called a compressor cascade. It's basically one row of blades from deep inside a jet engine. Now, the goal is always to make engines lighter, which means using fewer rows of blades. But if you do that, each row has to work way harder, and that creates a huge aerodynamic headache.
So here's the disastrous chain reaction.
The workload gets so intense that the air literally separates from the surface, right where the blade meets the engine wall. This corner separation is like a clog in a pipe. It creates a flow blockage. That blockage causes a massive drop in pressure, and that just absolutely kills the engine's efficiency.
So using their trusted simulation, engineers tested out a really clever idea. What if they blew a tiny jet of air from a little slot right before the spot where the flow was separating? The idea was to give the air a little kick to keep it stuck to the surface. And the result they got was, well, it was dramatic.
A 13% reduction in total pressure loss. Now, that might not sound like a lot, but in the world of jet engine design, 13% is a massive leap forward. It's a huge gain in efficiency, all thanks to a fix they perfected in the simulation.
And you don't have to take my word for it. Here's the final verdict from the research paper. The problem wasn't just made a little bit better, it was solved. The 3D separation completely disappeared. I mean, that's a total victory, one entirely in the digital world. So after that deep dive, what are the big takeaways? What have we really figured out about trying to master these incredible invisible forces?
Well, it really boils down to a three-part recipe for success. First, you need a blueprint you can trust, something that guarantees your digital world matches the real one. Second, you need a clear scorecard to know if you're winning. And third, once you have those two things, you can confidently test all sorts of wild, innovative solutions to really tough problems, and you can do it all before a single wrench is turned. You know, this technology is how we get quieter planes, more powerful wind turbines, and hyper-efficient engines. It's happening right now. It really makes you wonder, as these digital tools get even more powerful, what other invisible challenges are we going to solve? What new frontiers are we going to unlock?